Okay, well, thanks everybody, and thanks Rob for inviting me to talk. We've been hearing a lot about climate change these days, so it's a bit of a break to think about climate change in the past. There's three reasons for doing that. One is that there's a lot of new information from climate proxies and other data. The second is that we can learn about societal reaction to climate change from the past. There's a lot of data about what societies have done as climate has changed, so we can learn something about how societies respond to climate change, and maybe that's helpful for us as we look into the future. And the third thing is that the climate change that we've seen in the past, before the industrial age, really, is not driven by carbon dioxide change, but in fact is all the different natural oscillations of the atmosphere and volcanic eruptions and so on. So we get a picture of climate change before we were into the carbon dioxide era. I put this picture up from 1413 AD. It's from the Tres Heures of Jean, Duke of Berry, from the calendar month of March. It shows the first spring planting. And that's a time which is critically dependent on weather and climate. So we'll hear a little bit more about that later. But let's take a look at the big picture. Um, where we are in the grand scheme of things. The Earth was formed about 4.5 billion years ago, about the same time as the Sun. And we're about halfway through the Sun's age, if you want. It goes from being formed to growing to be a red giant, and then it declines into a white dwarf. But over most of its life, it's just as it is now, a normal star, and it's 4.5 billion years old as far as we know from the data that we have, and so we're about halfway through. So the real question is, can civilization last long enough to be part of the solar system until it disintegrates? That's a good question. It's a long time, 4.5 billion years. But if you want to see what 4.5 billion years look like, you can just go to Jack Hills in Western Australia. I don't know if any of you have been there, but here's a zircon from Jack Hills that is the oldest material found on Earth, and it's about 4.4 billion years old. So you've got it right there in Australia. You can see what it looks like and have a chance to visit the ancient history of the Earth. So let's look a little more scientific information. Here's the Earth's climate history. As I said, the planet was formed about 4.5 billion years ago, and the data that we have comes mainly this long-term data from ice cores and glaciology. But you can see, looking at the chemistry and the radiocarbon information, you can see what the temperature is like. The Earth has been warm for most of its lifetime. It was only until about 3 million years ago, over there on the right, that the Earth started to get a little colder than its average temperature today. And if we expand out this graph, you can see there, and I circled it in red, for the last million years or so, the Earth has been in an ice age up to about 20,000 years ago. These are the ice ages that were formed by the Earth's orbital changes, either the tilt in the Earth or the moving further or closer to the sun. Good scientific discussion of that has been published. So we've been in that up to about 20,000 years ago, and then if you if you look now at the end of that graph, I circled it in red there. Carbon dioxide rose from about 820 to about 860 parts per million, up to what we call the Holocene optimum. And for about 10,000 years, the Earth has been in a constant temperature mode, and this is the remarkable thing about the planet. If we expand that part of the graph and look out, you can see this is called the Holocene epoch. Holocene meaning recent epoch, basically. But you can see the Earth has been in a constant temperature, if you'll pardon the Fahrenheit, which I've been using for American audiences, but about 60, about 58 degrees, something like that, which is what you would expect from a greenhouse gas calculation with carbon dioxide about 860 parts per million. So for about 10,000 years, we've had the development of animals being domesticated. We've had organized agriculture, cities, domestication of horses, the pyramids, Bronze Age in China, the classic Maya civilization 2,000 years ago, and then printing press. And then at the very end, that red bit going up is the carbon dioxide rising the temperature. And we'll say a little bit about that at the end. But this is a remarkable 10,000 year period when the climate has been really very constant. It's allowed civilization and agriculture in particular, but in civilization as part of that to grow. And what we'll do is we'll talk just about the end of that graph. The Middle Ages, sort of from the 5th, 6th, 7th century up to the beginning of the industrial era, and take a look at what the data from modern climate proxies is showing us. So let's take a look at that. So here we're now focused on what we'll spend our time on during the talk here for about this is a 2,000 year period, and we'll look in more detail about sort of 500 to 1500. But you can see basically what we have is a very constant temperature with a number of wiggles and oscillations back and forth, and some uncertainty in the whole thing. This is only part of the picture, given the kind of average temperature of the Earth, because we've also had volcanic eruptions, which cause a cooling spike each time there's a volcano. So you can see the various spikes. Now this is schematically done. I'll show a picture at the end which tries to put all the major eruptions in place. But this now is really kind of the basic picture that we have for climate change in this period of the last maybe 1,500 years or so, as you can see. And what we'll do is we'll focus on three areas. Those two black lines going down are the volcanic eruptions in 536 and 540 AD. Then we'll talk a little bit about the medieval climate anomaly, which was a warm period in Europe, warm in Greenland in the North Atlantic, but cold in other places. But it had a big effect on society. And then from about 1450 up to 1700, we have the Little Ice Age, which was cold over most of the Earth, including in Australia, by the way. But this is the major things that we see in these oscillations are due to the natural oscillations of the Earth's ocean system, and we'll talk specifically about that. But first, I wanted to talk a little bit about how do we measure climate change. And well, let's just say, first of all, that climate and weather changes are similar to the modern era. The physics hasn't changed at all, but society was more sensitive to weather and climate change of the mostly agriculture society, isolated units. And as a consequence, societal resilience was weaker in the Middle Ages. Weaker, which means it was easier for the peasants to revolt and for a change of regimes to happen. But we're learning more and more about this. These new studies of environmental history with new data are helping us tease out the effects and the consequences. So as I said, let's look at where this information comes from. Weather chronicles have been going on for 1,000 years at least. Chinese records and Japanese records go further back than that. But here's a typical one. In the middle is one from England, and on the left there is one that was done in Spain. But here's what the record says, if you could read that fine print. On the 23rd, it rained. It was raining that night. On the 24th, there was a great wind. It kept snowing. Then the snow melted. It was cold. So whether there was snow or not, ice, whether it was cold or warm, these are records and the instrumental records that give us an accurate measurement with numbers didn't really start until about 1650. The longest instrumental record comes from central England, with thermometers being used about 1650, as I said. Another indication of the temperature is when was the grape harvest, and of course the grape harvest date is well known because that's the time that the town had to pay the vineyards. So they've got that in the town records. And I picked another picture from the Tres Richeurs here to show you the grape harvest date, and I like this one because you can see right in the middle there, next to the cart with the grapes, is a peasant who's mooning the audience, typical of some of these drawings that are done. But if you look at the graph on the right, you can see that the grape harvest is either in the late September and varies all the way down to late November. And the colder it is, the later the date. And so this also gives a record of temperature. This is from 3 different regions in France: Burgundy, Ile-de-France, and Alsace. But you can see there's a nice accurate record here that can be used to give a sense of what the temperature was. Well, what's new? We have a lot of new scientific data on climate and weather history. Here's 4 of those things put into one picture. Is ice cores from glaciers and from Greenland and from the Antarctic. Caves, stalagmites that collect over thousands of years, the records of chemicals dripping down. And then tree rings. Tree rings go back about 1,000 years for the longest ones, taking a core, and you can see that one that there goes back to the 16th century. So that's one set of proxy data, and we have more and more of this. Some of the ice cores will give us data going back almost 1 million years. There's 750,000 year ice core that was taken from Antarctica. But we also get data from the ocean, looking at ocean temperature, which is because the ocean takes a long time to mix and to overturn. The deep temperatures will reflect temperatures from maybe as long as 1,000 years ago. And then we get records from corals, a lot of good records around Australia from coral skeletons, boring into the coral. The growth of the coral depends on what the temperature was, what the chemicals are, and that's recorded in the various layers that are laid down each year. So just like tree rings, coral skeletons also are valuable for this. The distribution of these proxy measurements is really pretty broad. You can see the green here all over the map is from tree rings. The yellow is from corals. The orange is from glacier ice. The red is from marine sediments and some documents. But you get the idea that we have a global distribution of these proxy records. And we also have, well, you can see there's a couple of places where we don't have much in the way of these proxy records, both in South America and then in the Sahara Desert of Africa. So we have pretty good global distribution. That covering in terms of time, we have good coverage. As I said, the tree rings go from now all the way back maybe 1,000 years, and some of the ice cores there in light blue, as I said, go back close to 1 million years from Antarctica. So there's a very good coverage of time frame from these various new measurements that have been made and that are being collected and studied. And you can look at the radioactive decay of the radiocarbon elements, for example. So let's look at our graph again here and talk about these 3 different areas. And I first talk about the volcanic eruptions. Two of them. You can see there are many others, but this gives give you an idea of what the volcanic eruptions did and what the effect was. You're familiar, of course, with volcanic eruptions putting lots of dust, sulfur particles, and aerosols into the atmosphere. And if you look at this little GIF image carefully, you can see the light. There's lightning strokes. So lightning is also something that is a part of volcanic eruptions, which were pretty frightening to people in antiquity and the Middle Ages. And here's what happens, as I think you're mostly aware of: ash and sulfuric acid going into the atmosphere, actually above into the stratosphere, reflecting sunlight back into space. As a consequence, there was a cooling effect underneath that cloud, which can extend halfway around the Earth, and less rainfall over ocean and land. So this has an immediate effect, and it lasts from a few months out to a couple of years. Well, this huge eruption that took place, actually there were two volcanoes, one in Iceland and one in El Salvador. But here's one of the records that says in the year 536, 537, the sun was darkened. The eclipse lasted a year and a half. Each day it shone for about 4 hours. The light was just a feeble shadow. People were concerned that it might not return to this state of original light. Problems with fruit, and the wine had a taste of sour grapes. So this has an immediate impact on the agricultural societies, obviously. And here's a modeling study that tried to look at what the temperature change would be. And you can see a couple of degrees Celsius there, right at 536. And then from the second eruption at about 541, big eruption in Iceland, big eruption in El Salvador, as they trace back exactly what the chemicals were. So these two temperature drops, and this is what we expect the temperature looked like. This was the temperature in 536 to 545 that's been done by modeling studies that took that temperature and then put it into the atmospheric circulation. And you can see the big impacts that we had here. Here's the drought, crop failures, summer snow in Asia, harvest was delayed, dense dry fog in the Middle East. This is the summer picture at that time, but even so, you can see the number of cold areas. So this is something that definitely has a big impact on agriculture and a big impact on society. If you try to understand about how this fits together, the climate changes from the two eruptions force marginal agricultural societies in Northern Europe to face multiple years of crop failure in a single decade. So you have starvation, certainly, as well as colder times. Now you can ask the question, was the cold weather caused by the eruptions a factor in the spread of the bubonic plague during Justinian times that spread throughout the Mediterranean, killing 35 to 55% of the population? We don't really know cause and effect, but certainly these weather-induced agricultural impacts were among the causes of widespread societal changes in the 6th century, which marked the end of antiquity and the beginning of the Middle Ages. So these volcanoes have had similar effects. Volcanic eruptions have had similar effects over the years, and still, as you know, can have a big local impact. Well, let's look at the second piece of what we wanted to talk about today, and that's the medieval climate anomaly, going from about 750 out to 1200, something like that. And here's what it looks like from a modeling study. Michael Mann, who has done a lot of work on climate modeling in the modern times, took all of the climate proxy data and fed it into models. And this is, as far as I know, the only really global map that's been done of the medieval climate anomaly. You can see a very warm, and here's some of the indicators there, very warm in the North Atlantic. It was actually warm relatively warm in Europe. This is temperatures relative to today's temperatures. So in fact, the North Atlantic was warmer than it is today during the medieval climate anomaly. It was somewhat warm in Asia, wet in India, dry in North America, cool in the Eastern Pacific, dry in Africa. So this had an important impact on society. And in fact, here's some of the things that happened during that time. Certainly drought from the dryness in North America, which had effect on the Mayan civilization. The Vikings, with that warm North Atlantic, moved up to Greenland and then on to North America. Vineyards prospered all the way as far north as England and Norway. And because it was relatively warm, agriculture flourished and the European population grew. And so there was major changes during that period. There was wheat cultivation at higher latitudes in the Far East, with farmers spreading into northern Russia. You're seeing that today, as a matter of fact, as Chinese farmers are welcomed by Russia into Siberia. And the Mongols conquered large parts of Asia. One of the advantages of the warmer weather makes it easier for the Mongols, who had these large contingents of horses that needed grass that was growing plentifully through that period. And so it was easy for the Mongols to do their conquering. So that's the medieval climate anomaly. And here's an example of the Viking expansion. You can see how they moved and created farms. It was mostly farming that they were, and agriculture that they were promoting over those times. But they moved to Iceland and set up settlements there. They moved to Greenland and set up 2 or 3 settlements towards the tip there. And actually, there's remnants of their visits in North America. So this was an important impact of that warmer period, that very warm North Atlantic that appeared during that period that led to the expansion of the Vikings. So that's the medieval climate anomaly. Then we can move on to the Little Ice Age, and now it becomes colder. But I thought it would be useful to look at this. Here's the medieval climate anomaly. It's the one we just saw. It's the North Atlantic is warm, America is warm and dry, and you can see that. And now I'm going to merge this slowly. It took 150 years for it to happen, but we'll merge it slowly from the medieval climate anomaly into the Little Ice Age. I don't think anybody else has shown a graph quite like this, so I'll show you how that goes. Here we are. There you go. So you can see how it moved. Now I'm just going to go back again and show you that. Let's just go back here. Yeah, and now I'll just do it again, just so you can see it a second time. There's the merging, and it took, as I said, 150 years, as you can see on the graph. But now we have a much colder North America, much colder Europe. This is a time when everything was frozen, and the North Atlantic is still warm, but it's not as warm, and it was certainly colder in Asia. And here's some of the impacts that we saw during that time. The Vikings left Greenland. The Thames was frozen over in ways that it hadn't been before. There were long winters, short, wet summers. Glaciers were advancing in the Alps. We had droughts in Africa, multi-year droughts in Asia, and actually glaciers were advancing in New Zealand and also down in the Andes. So this was a definite change in what had happened to society. And here's an example. This is a Bruegel painting. It's the biggest one from 1365, times when you could skate from one end of Denmark to another. And here's a picture from the Trébucheurs showing the wintry scenes that were common during that period. But the Vikings also left Greenland, not so much because it was cold, but because, in fact, the rainfall decreased steadily over that period. It got drier and drier, and so it was harder for the Vikings to harvest land animals, which they had been doing, and they changed their diet to marine mammals, as you can see from the remains left from the villages that were there, and they had to rely on marine mammals, which is not so reliable. There's rough waters all around Greenland, and they eventually had to move back into Europe. Drought is still a concern in Greenland, but today they just import food as opposed to what the Vikings could do, which was simply try to find more food. So it's a change in what has happened there. So just quickly to say about some other parts of the world, the Tang dynasty, which ended in 907 AD, was a dynasty that could have had an effect, could have been affected by the colder winter. It was just definitely true that in China, the relation between winter and summer monsoons suggests that the dynastic transitions occurred when the summer monsoon was weak with less rainfall, and this was phases of crop failure and famine, and so reduced rainfall led to crop failure and famine. This made it easier to have popular uprisings. Of course, the uprisings depend also on the leadership and other things that are happening in the country. But certainly, crop failure and famine are a contributor to this. The last Tang emperor was deposed in 907, and there seems to be a relationship between that period, that ending of about 900 AD, that the intertropical convergence zone, which was a tropical rain belt, moved south away from China and led to weaker droughts and summer rains. Now, the reason we think this has happened, the same thing happened to the classic Maya civilization in Middle America. Almost the same thing. The comparison of the records from China and North America shows a general shift towards drier climate about 750 AD, which lasted till almost 900 AD. And it coincides with the final stage of the Maya collapse, as well as the end of the Tang dynasty. So it seems possible that these major shifts circum-Pacific, all the way across the Pacific, in the position of the intertropical convergence zone, affected events in both countries. We'll talk a little bit about that later, but here's a picture of the Maya sites. I wanted to show this because this is one other kind of new information that comes not from drilling, but actually getting a very accurate picture of the shape of the surface of the Earth by flying LiDAR flights. That the LiDAR pulses actually are able to penetrate the forest, and they can give this very detailed picture. You can see that of one of the classic Maya sites. It's in Belize at present. There's two different pictures here to show the details that you can see from the LiDAR mapping. And if you look at the map of the intertropical convergence zone, you can see that both the Maya civilization and the Tang dynasty were closely related to that as the ITCZ, as we call it, moves north and south. But the whole thing moved south at about in the late 900s and early 900s, actually. Moved to the south, and it deprived both of these civilizations of the rainfall that they would expect, and so that definitely was a stressor on the civilization. Well, that leads us into the whole question of how do we explain the various oscillations that we see in the Earth ocean system, and then how that's affected by the sun. The sun has sunspots, as you know. There's the sun rotating, and when there are more sunspots, we have a little more active sun, and you get more light out. And in fact, the sun's oscillations, there's a picture of the oscillations. Solar activity does vary up and down depending on the time. There's a regular 12-year solar cycle, and then there are longer cycles which have differing impacts, fairly minimal, but differing impacts on the Earth. And of course, the Earth system itself has a lot of different oscillations. In fact, if we just list a few of these are things that we've learned that do exist. North Atlantic Oscillation, the El Nino, you're familiar with that, being in Australia, the Atlantic Multicadal Oscillation, the Pacific Decadal Oscillation, and several others, and not listed here. So lots of different oscillations of the system. In fact, we can look at a couple of these. Here's the North Atlantic Oscillation, and I like to show this one with this particular picture because you can see that warm area off Greenland, and exactly what we saw during the medieval climate anomaly, and what led the Vikings to go to Greenland and then on to North America, because it was very warm at that time. And so you can see down below the long-term graph, there's lots of oscillations, or lots of different periods of time periods in this oscillation, as you can see from the graph. But it was in the warm phase, in this what was called negative phase, but it's actually warm phase, from 1100 out to 1400 during that medieval climate anomaly, and then it shifted into a colder regime. So it's believed that the North Atlantic Oscillation is an important driver of the medieval climate anomaly and the Little Ice Age, but it's not the only one. If we look at the El Nino, there's obviously an influence on North America during the La Nina, which is actually what we're in today, is La Nina. We're just coming out of one with a variable jet stream and dry over most of the southern United States and Mexico. Whereas El Nino tends to bring us wet weather and storms in the western U.S. and over Mexico. So and you can see from the graph below that there's a lot of different oscillations of the El Nino. There's a 7-year oscillation, and then there are longer ones. They tend to come together, so we have strong episodes and weak episodes. But the El Nino has been recorded for a long time, more than 1,000 years. As we look at the impact on South American fisheries, we can see that record. But once again, lots of different oscillations, and this is what contributes to that picture that we saw of what the overall temperature looks like over the past 1,000 years. So dry and wet, that's the thing to remember about El Nino. But the El Nino, I just showed impact on North America there, but it has an impact all across the world. You're familiar with the dryness from El Nino in Australia. But if you look all the way over to the left of this graph, you will see in Africa, in East Africa, wet, and just a little bit north, dry during that period. And as you know, these are the areas, these areas right there, headwaters of the Nile, and they will determine what the flow of the Nile River is. And in fact, it is possible to go back over 1,000 years and correlate the El Ninos and the outflow of the Nile. So you see this nice global impact of these various oscillations that we see. Now, that's not the only one. There's an Atlantic multi-decadal oscillation, which tends not to be so strong in the period of the medieval climate anomaly, but quite strong during the Little Ice Age. And so what we believe is that the North Atlantic Oscillation was strong during the medieval climate anomaly, and it was the Atlantic multi-decadal oscillation that was strong during the Little Ice Age. So we're starting to get some handle on cause and effect during these periods. Then the final thing I wanted to show you about the ocean here was the fact that the ocean takes a long time to mix and to overturn. And in fact, here's a nice diagram that was put together by NASA, showing this. You can see the waters of the Gulf Stream moving north off the coast of the United States. Those waters move north, they cool according to what the temperature is in the North Atlantic, and they sink. And you can see those arrows sinking down and then flowing back to the south those are colder waters now that have they've gotten cold. They sunk, and now they're flowing back through the Atlantic, and underneath that warmer water, which is flowing north. And these waters, which reflect the temperature of the North Atlantic, are now flowing to the south. They flow all the way down around South America, and then curve, joining the Antarctic circumpolar current, but still remembering that temperature from the North Atlantic. And they curve down, and you can see them moving further and further as they go. Some of it surfaces in the Indian Ocean, and then some of it comes around Australia and actually surfaces in the Pacific. But you get some sense of that. What's interesting is that because it takes a long time, the ocean has a long memory. And in fact, as I said, between the 9th and 12th centuries, the North Atlantic region was warmer before the Little Ice Age settled in around the 16th century. So that warmer water cooled and sank, still remembering that temperature that it had. And as part of that ocean circulation, the warmer water sank and began what is now it's a 1,000-year journey from the North Atlantic all the way around past the Indian Ocean and then up into the deep Pacific. And in fact, when the water in today's deep Pacific last saw sunlight, the world was still cooling from the Little Ice Age. And in fact, if you sample deep water in the Pacific, there will be some remnant of that temperature when you feel the water. And I can remember sampling on the deep sea drilling program. We did some deep water sampling off Hawaii, and I remember the cold water running over my hand from the Nansen bottles. But I didn't think at the time that this was related to the North Atlantic. But in fact, these things are all connected. So just to finish up now, there's been a very nice recent record put together from tree rings and corals of Australia temperatures. And in fact, in the lower left, you can see where these were taken, tree rings in green and the blue from the corals and some cave records. But you can see we have reflected from those mostly northern hemisphere records. You see pretty much the same thing in your Australia record, not quite as prominent, but you can still see the cooling around 1500 and the same kind of waviness, and of course the rise at the very end. But this is more evidence that the Little Ice Age, the cooling period, extended from the north into the higher latitudes of the southern hemisphere. So that's our picture. Volcanic eruptions, the medieval climate anomaly, Little Ice Age, these various oscillations all coming together, and that gives you a sense of what's the science, what's the impact, and this is the kind of graph and data that the modern people who study what they call the science of the human past. There's a number of new programs, including one at Harvard, that tries to pull all of this data together. Here's what the actual scientists would be looking at. It's a graph more like this, which shows you this is tree rings in detail, and you can see that there's much more spikiness in the record. Down at the bottom of this shows the volcanoes, so you can see there's many of those. The green are major shifts in civilizations. The blue are different societal impacts. The stars are major famines, and in fact, you can see that many of those stars occurred right at the time of a cool temperature, and many times with a volcano. But it's this kind of data. It's a rich storehouse of data that's really valuable for scientists to study together. And so it's a brand new field of history, but a very exciting one. So just to finish up now, I promised to talk just a few minutes about the red blip at the end, and this is what we're starting to call what geologists are thinking about calling the Anthropocene. The Holocene being recent epoch, the Anthropocene being the human epoch, if you want. Typically, geologists have used these names and you've heard other such names, Pliocene or Pleistocene or Eocene, to represent geological ages. Is it right to talk about human impact? And so there are committees that decide these names are talking about that, but there is no question that we are changing the climate, and you can see that just from the red blip over the past 10,000 years. We've come out of that warm embrace of the 10,000-year Holocene climate, and we're rapidly rising out. And if we just to remember all the things that happened in the Holocene, and so if we could just have a little epilogue of where we are today. Since the beginning of the industrial age, fossil fuel energy has been driving climate change on a global scale, and rising temperatures are leading us into a climate regime that is different from anything we faced during their existence. Now, up to now, as we've just discussed, and that's a reason for thinking about the Middle Ages, climate change has come from natural fluctuations of the Earth system. But from now on, we have a new driver in addition to those systems, and we don't know how it will interact, but humans releasing greenhouse gases from using fossil fuels. As I said, Earth scientists have recognized this change with discussions of a new age, the Anthropocene. Nations are trying to take heed and to take actions, but actions are slow because and we know massive energy infrastructure changes are needed, and it takes a long time to do that. Can we move fast enough to avoid major climate change? Well, we don't know at this point, but we're at a turning point for human civilization. So that's why it's good to look back into the Holocene and to see what has changed, to understand the natural changes, and then to use that as a basis to look forward and what we might see. If you want to read more about this, here's just 4 books. There's lots of literature out there now, but the Nomad Century gives a sense of climate migration and how that's going to be driven by a warmer world. The Human Planet is a very nice long discussion of how the Anthropocene has come about and why it's different from what we've seen in the past Holocene. Climate and Society of Europe is a relatively new book that focuses just on the last 1,000 years. In Europe, what were the changes and what were the details? How do you relate natural climate fluctuations to actual societal fluctuations? I just did a very brief overview of that, but here's where you can see the detail of different civilizations and what they did. And finally, if you want to look into the history of the Vikings, you can read this Children of Ash and Elm, a book that my wife Emily pointed out to me. Very nice history of the Vikings and their various migrations and so on. So that's just a little summary. Lots of things to read, but that gives you a little summary. Now, just let me finish up here. I just want to point out that I'm trying to do my part in not putting more CO2 into the atmosphere, even as I do my presentation. So this presentation is carbon neutral. And in fact, all energy-related pollution created during the making of the presentation was neutralized through energy certificates from TerraPass. What TerraPass does is they use funds that are donated to close down old oil wells, which are methane emitters. So this is a definite positive impact on global warming, and I can buy enough, and I can figure out how much carbon I emit driving back and forth to get the paper for printing out the presentation, or for running the electricity of the computer. It's not a lot, but it's my contribution. Anyway, there we are. So that concludes the talk, and I will be happy to answer questions.